We are going to review random variables in this and the next 3 lectures. I would like to cover the definition, the probability laws that govern random variables, expectations and moments, the common discrete and continuous distributions that we will encounter in this course, and how they arise and their interrelations, change of variables, joint distributions, functions of random variables, and the convergence of a sequence of random variables. In addition to the recommended text by Ang and Tang, I'd also like to recommend the book by Sheldon Ross and the book by Papoulis and Pillai for further reading. Now, a random variable is a measurable function defined on the sample space. So it maps events from the sample space onto intervals that you see on the screen. And we discussed measurable functions in the previous lecture. Informally, when the possible outcomes of an experiment or trial can be given in numerical terms, and they can be assigned probabilities obeying the axioms of probability, then we have a random variable in hand. So when an experiment is performed, the outcome of the random variable is called a realization. A random variable can be discrete or it can be continuous, and as I said, it's governed by its probability laws. If a quantity varies randomly with time, we model it as a stochastic process. A stochastic process can be viewed as a family of jointly distributed random variables. If a quantity varies randomly in space, we model it as a random field, which can be thought of as a generalization of a stochastic process in 2 or more dimensions. Now, the probability laws of a random variable, there are 4 ways to describe it. The cumulative distribution function, or the CDF, the probability density or the probability mass function, depending on whether the random variable is continuous or discrete in nature, the characteristic function, and the moment generating function if it exists. Now, the CDF is the probability that our random variable assumes values less than or equal to little x. Our convention is to use uppercase letters to denote random variables like x, y, z, and lowercase letters like a, b, c, and little x, little y, little z to denote its realizations. So the CDF, it starts from 0, ends at 1, and it's a non-decreasing function. If you want to find the probability that the random variable x takes on values between a and b, strictly greater than a and less than or equal to b, it is the difference of the CDFs evaluated at b and a. And if you would like to find out which of these corresponds to which axioms of probability, so this statement corresponds to the first axiom, this statement corresponds to the second axiom, and the last is the equivalent of the third axiom. The density function is the derivative of the CDF, or equivalently, the CDF is the integration of the density function. The area under the density curve is the probability that the random variable takes on values between the limits, as I said. You can also think of the density function as it gives a measure of the random variable taking on values around that particular x. So its fx dx is a small probability. Its properties are it's a non-negative function that integrates to unity. For discrete random variables, we have the mass function. So it's a probability that the random variable takes on that particular value, xi, lowercase xi. You can also identify the PMF from discrete jumps in the CDF, as you see here. And if you sum all the PMFs, these are all non-negative numbers. If you sum all the PMFs, you get the value of 1. It's possible to describe mass functions as density functions by the help of the delta function. So as you know, the definitions of the delta function as I have put on the screen. So you can describe the density function equivalently as the sum of the individual PMFs multiplied by the delta functions, as you see on your screen. So I'm going to put 3 figures here, and let's see if you can identify if there's anything wrong with these. So the first one is a density function. The second one is CDF of discrete random variables, and the third one is also another kind of CDF. So the first one is actually not right. The density function can never be negative. The second one also has a problem because the CDF can never go down. As you can see, at 7 it goes down, and the last one, it's fine. It's non-decreasing, so it's okay. And this is a particular case of a mixed distribution. So this is where sometimes the random variable takes discrete values, and in other cases it takes continuous values.